In section 6.2, we're going to discuss the confidence intervals for the mean, much like we just did in the last section, but now we're going to do it under the assumption that the population standard deviation sigma is unknown. So some assumptions made in the last section were based on knowing the population standard deviation sigma or using the sample standard deviation s, as long as the sample size was at least 30 or more. However, in general, if sigma is unknown and s is used as an estimate, the sampling distribution of x bar only approximates a normal distribution. It's not going to be exactly a normal distribution. We're not going to exactly be able to use z-scores. Rather, what's going to happen is the sampling distribution of x bar follows what's called a t-distribution. Okay, so the x bar again was the sample mean. So rather than the normal distribution, we're going to work in what's now going to be called the t-distribution. And this is going to be the formula for the t-value, much like we had a formula for the z. If the distribution of a random variable x is approximately normal, then t is equal to x bar minus mu over s divided by the square root of n. If you compare this to the formula for z in the last section where we did that for the sample means, this is very similar to that. Just notice we're using the letter s instead of sigma for the sample standard deviation. The critical values of t, much like we did before, will be denoted t sub c. And the t-distribution, like we're going to see here in a second, is very similar to the normal distributions, but it does have a few certain properties to set it apart. We'll have to kind of keep track of those as we go along here. So the properties of the t-distribution: 1, much like the normal distribution, the mean, median, and mode is equal to 0 when we have it in the standard normal distribution. The t-distribution is bell-shaped and symmetric about the mean. The total area under the t-curve is equal to 1. So far nothing here is much different than a normal distribution. Here are the big differences. The tails of the t-distribution are thicker than those in the standard normal distribution, and the standard deviation of the t-distribution varies with the sample size but is always greater than 1. The t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. So here's another new thing to talk about. The degrees of freedom are the number of free choices left after a sample statistic such as x bar is calculated. When you use a t-distribution to estimate a population mean, the degrees of freedom are always equal to 1 less than the sample size. We're going to denote degrees of freedom as df. It's equal to n minus 1. Here's what's going on in a t-distribution curve. As the degrees of freedom increase, the t-distribution approaches the normal distribution. For 30 or more degrees of freedom, the t-distribution is close to the standard normal distribution. We will approach the t-distribution much like we did the normal distribution. There's a table of values that tell us the area under the t-distribution, and these areas can be used for the same type of percentages and probabilities and all the things we were doing before. However, the table is going to have more going on in it than we saw in the normal distribution table. Also, under certain conditions, we won't have enough information to look it up in the table. In these cases, I'm going to show a little bit of the calculator and how we can use it to also do some of these calculations. Turns out we could carry some of these ideas over to the normal distribution because the calculator has those functions built in as well. It's just for us, it's never been more for us to do than just look it up in the table usually. So the calculator wasn't usually too big of an aid in the process, but here it will be in some cases. So let's look at some values here and some examples. We're going to try to find a t-distribution with 3 degrees of freedom, and we're going to compute some of these probability values. Before, what we would have done if this was z and the normal distribution is we'd look it up in the table, find the areas, and that would help us find the probabilities. Here what I'm going to do is look, this is a TI-84 calculator, and to do this in the TI-84 calculator, there's a function called tcdf. This is for the t is for the t-distribution, and CDF stands for the cumulative density function. Terminology we haven't used here, but the density function we did mention a little bit before. But we can use this to calculate the area under the t-distribution without having to look it up in a table. So in a TI calculator, you have to press second, then the VARS/DISTR button to get to this screen that I have here. Then you go to option 6, which is the TCDF option. Now if you go there, it's going to look something like what's on the right. It gives you a lower, upper, DF options to plug in numbers for. And so for this instance, we're going to be able to plug in these numbers: negative 1.5 on the lower, 1.7 on the upper, and the degrees of freedom is 3. And then if we hit enter, we'll get over to the other screen here where it calculates this particular value. And so what I'm seeing here is something approximately 0.791. So under the t-distribution, the probability that t is between negative 1.5 and positive 1.7 is approximately 0.791. Let's do this with another calculation, but here we're going to do the probability t greater than or equal to negative 1.13. So let's return back to the same menu and let's enter the following inside there. So in the lower, I'm going to put negative 1.13. On the upper, I'm going to put something a little different. It's going to go 1E99. This is just for the calculator, like the largest number we could put in here. And it's meant to show the other side of the curve on the right side, the greater than side, without ever stopping at a different number. Degrees of freedom is 3. Now, if you're doing this on your own, you want to know how to get that E that I put there, you have to press the second and then the comma button on the calculator, and I have a little picture of what that button looks like to get that E, and that scientific notation button is what that is. So if we do that and then go to the calculation screen with it, we'll get a value of approximately 0.830. So that's the probability in the t-distribution that t is greater than negative 1.13. It also corresponds, just like we did in the normal distribution, to the area under the curve on the greater than side as well. And a similar process could be used for the less than direction. I went ahead and plug the numbers in slightly differently. You'll notice on the lower I put negative 1E99, and on the upper I put negative 1.13. So it's a little bit different, but if we plug those in, and we can get the calculation here of probability of t less than negative 1.13, approximately 0.170. On this next one, we're going to consider the t-distribution with 30 degrees of freedom and find the value of c such that the probability of negative c less than t less than c is equal to 0.95. Now in this case, we can go over to the t-distribution table and look this one up. Actually, we have the right information for it now. So here's the t-distribution table, and I have this one posted online as well, if you'd like to reference it. It kind of shows you the areas we're dealing with here. We'll talk more about some of these different parts as we go, like the left tail and the right tail, though those kind of correspond to the left and right areas we had talked about on the normal distribution curve. But for us, we want to look up some of these numbers here. For instance, we have like this 0.95 level of confidence, and the degrees of freedom are over here on this column. So let's go over to our example and see what we're doing there with the table. So in the t-distribution table, what we're going to be able to look up is this level of confidence. We're going to talk more about that here in a second, but in our case, that 0.95 that it's equal to is going to be also the level of confidence here. So we start with that column, and then we're going to go down till we find the degrees of freedom for 30, and then correspond the two together here, and we get a value of 2.042. And so what that value represents for us is the value of C. C is equal to 2.042 in order to make this probability value equal to 0.95. I mentioned much like the z-score table, we have critical values for the t-distribution. So let's find critical values for a 95% confidence level when the sample size is 15. Okay, and again, we're denoting critical value here by T sub C, kind of like we did Z instead of that, we're using the letter T. So much like the Z-scores, we're going to look it up in the table. Start by finding the degrees of freedom, which the degrees of freedom df is equal to n minus 1, which our sample size minus 1 would be 14 in this case. And so when we go over to the t-distribution table, we'll be able to look up the column for degrees of freedom and level of confidence. And notice how each row has a degrees of freedom value from 1 onward up to some fairly large numbers toward the end. So under these conditions now, we're using the 95% confidence level, which will be the 0.95 that we're going to look up in the table. df, degrees of freedom, is equal to 14. And so in the t-distribution table, this would be located here. On the column 0.95 level of confidence, the row for 14 degrees of freedom, 2.145. So what we can say is, given that now we know the critical value T sub C is 2.145, we can also tell that since we're using 0.95 as our level of confidence, that also corresponds to the area inside the curve between the critical values negative T sub C and positive T sub C, much like we're going to see in this picture here. So it looks like a normal distribution curve, but it's not exactly, so that's why we're using the t-distribution. So between negative 2.145 and positive 2.145 is 0.95 is the area, and that's also called the confidence level. Also, we use the lowercase c to denote our 0.95 as well. So constructing a confidence interval for mu when sigma is not known using the t-distribution is very similar to constructing the confidence interval for mu when sigma is known using the standard normal distribution. We start with a point estimate using x bar and using a margin of error e. The formula for e is virtually identical. The largest difference here is that we're using a t-distribution and the critical values t sub c instead of the z-scores. So it's margin of error equal to t sub c multiplied times s over the square root of n. You might also note that we're using s instead of sigma to denote sample standard deviation versus the unknown population standard deviation sigma. So here's kind of the overall process we see here. To construct a confidence interval from the population mean when sigma is unknown, we're going to verify that sigma is not known, but we also need to verify the sample is random and the population is normally distributed or n is greater than or equal to 30. Then we're going to find the sample statistics, n, which is sample size, x bar, sample mean, and s, sample standard deviation. So notice how s is equal to the formula over there. That was our formula for standard deviation. Then we're going to identify the degrees of freedom and the level of confidence and the critical values t sub c using the degrees of freedom is equal to n minus 1. And we're going to mostly just be looking it up in the table to get the t-distribution information. Then we're going to plug this into the margin of error formula. And then from the right and left endpoints, we're going to take the sample mean x bar minus the margin of error e and x bar plus margin of error e. And that's going to give us our interval for the confidence interval, and the population mean would then fall within that confidence interval with a certain level of confidence. So let's look at this example here. Randomly selecting 16 coffee shops and measuring the temperature of the coffee sold at each. The sample mean is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. We're going to construct a 95% confidence interval for the population mean of the coffee sold, assuming the temperatures are approximately normally distributed. So our first number is our sample size, n is equal to 16. Our sample mean, x bar, is equal to 162. Our sample standard deviation, s, is equal to 10. That means, and our confidence level for the lowercase c is equal to 0.95. So putting this all together, we have these values. We're going to next need to do the degrees of freedom. So df is equal to 16 minus 1 equal to 15. Now we're going to go to the table and look it up. The numbers we need to look up in the table, first off, for level of confidence are 0.95. And then the degrees of freedom, df, we'll look that up for 15. And then that gives us our value here for our critical value, t sub c, equal to 2.131. Okay, and now we're going to move over to our margin of error formula. For that, we need three numbers, n, s, and our critical value, t sub c. And so we're going to plug those numbers in. We'll get e is equal to 2.131 times 10 over the square root of 16. And that's all approximately 5.3. So that's our margin of error in this case. To do the confidence interval with this information, we'll take our sample mean x bar. For the left endpoint, we're going to subtract it, 162 minus 5.3 to get 156.7. For the right endpoint, we'll add it, 162 plus 5.3 to get 167.3. That gives us our confidence interval for the mean, population mean mu, 156.7 less than mu, less than 167.3. Let's look at another example. We'll do the same thing here and try to find some confidence intervals as well. The example is randomly selecting 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. It gives us our sample mean of 9.75 days and sample standard deviation of 2.39 days. We're going to construct a 99% confidence interval from this information. Okay, let's write down what we know here. Our sample size n is a sample of 36 cars. And since n is greater than 30, we're safe to do what we're going to do here because there were two criteria. Either n was greater than or equal to 30, or we knew that there was a normal distribution involved with the population. So we're good to go here. We don't know the population standard deviation though. That's why we're going to use the t-distribution on this one. Our x bar would be equal to 9.75, and our value s for sample standard deviation would be 2.39. Our confidence level, which will be lowercase c, is equal to 0.99, and our degrees of freedom, df, will be equal to n minus 1, so 36 minus 1 equal to 35. Our first step in the process is to find the critical value t sub c. We're going to be able to look that up in the table. So let's run through the process of looking this up in the table. Our degrees of freedom is 35 for df, and our level of confidence is 0.99. So let's go down this column for the level of confidence c until we get down to our degrees of freedom of 35, which should be down here. There it is. Okay, so going across here, we can see that our critical value, t sub c, is equal to 2.724. All right, now with that taken care of, we can plug this into the margin of error formula, E equal to t sub c times s over the square root of n. So that's going to be equal to 2.724 times standard deviation 2.39 over the square root of 36. And that comes out all to be approximately 1.09. And that's our margin of error E. With that margin of error E, we're going to construct the confidence interval. And to do that, we're going to take the x bar minus E, x bar plus E. So our sample mean 9.75 minus 1.09 9.75 plus 1.09. And that gives us 8.66 and 10.84. And those go together to give us the confidence interval 8.66 less than mu less than 10.84. So this is a summary of now where we've made it up to now, with all the information coming from the central limit theorem to when we did margin of error using either the z-score table or the t-distribution table. First off, you want to check, is the population normally distributed or is n greater than or equal to 30? If either one of these are not met, then we cannot use any of our tables, any of our methods to find margin of error. Those are at least one of those criteria have to be true. If one of those is true, then we check to see, do we know the population standard deviation sigma or do we not? If we do know sigma, then we can use the standard normal distribution to get our margin of error using the z-scores and our critical values z sub c. On the other hand, if we do not know sigma, then we have to use this other formula for margin of error using the critical values in the t-distribution and using also this other new thing, degrees of freedom n-1. Just look at an example and figure out what would we do, what would we use? Could we use z-scores? Could we use t-distribution? What would we do here? It says randomly select 25 newly constructed houses. The sample mean of construction cost is 181,000. The population standard deviation is 28,000. Assuming construction costs are normally distributed, should we use the normal distribution, the t-distribution, or can we use neither of the two? And so what we're going to be trying to do is construct a 95% confidence interval using margin of error basically for the mean construction costs of the population. Well, first off, first criteria, is the population normally distributed or is n greater than or equal to 30? Well, we see that our sample size is not greater than 30. Our sample size is only 25, but it does mention explicitly assume that the construction costs are normally distributed. So that means our population is assumed to be normally distributed here. So that criteria is set. So even though the sample size is less than 30, we can still use either the normal or the t-distribution. Second thing, is sigma known? Did they tell us the population standard deviation? Indeed they did. So knowing sigma means we would use the normal distribution instead of the t-distribution. We would use z-scores.